Welcome all. Now we are discussing Lemma 7.2. Let X be a linear space over K and Y be a subspace of X, which is not a hyperspace in X. If X1 and X2 are in X but not in Y, then there is some X in X such that for all t element of closed interval 0, 1, tx1 plus 1 minus t into x element of not an element of Y, and tx2 plus 1 minus t into x not an element of Y, that is the line segment joining x1 and x not in Y. Similarly, line segment joining x2 and x not in Y. If X is a normal space, then the complement Y complement of Y is not is connected. So let's consider the proof. We have X a linear space over K and Y is a subspace of X, but Y is not a hyperspace. Okay, a hyperspace means it is a subspace which is the largest proper subspace, that is called hyperspace. If X is finite dimensional, then the dimension of its hyperspace is just one less than that of X. Okay, now let x1 and x2 element of X but not in Y. Then we have to select an element X in X such that the line segment joining that element with x1 and x2 is not in Y. Okay, if tx1 plus 1 minus t into x2 is not in Y for all t element of open interval 0, 1, then what happens? Then we can take that element X as x2. Okay, then the result is true. Okay, whatever the case is, we have to select a point X in X such that the line segment joining x1 and that point not in Y. So if this is happens for x1 and x2, then we can choose x equal to x2, and similarly we can choose x equal to x1 in the other sense. Okay, if not, if this is not the case, then what happens? Assume tx1 plus 1 minus t into x2 is element of Y for some t element of closed interval 0, 1. Okay, let that point be S. Okay, that is there exists some S element of open interval 0, 1 such that S x1 plus 1 minus t into x2 1 minus S into x2 is an element of Y. This implies the point x1 is an element of span of Y comma x2 and x2 is an element of span of Y comma x1. This means that span of y comma x1 is equal to span of y comma x2. But we know that y is not a hyperspace, in X, and so we can write that span of y with a single element is not equal to X, that is not equal to span of y with x2. Okay, this is true since y is not a hyperspace. Okay. Now choose an element from x minus span of y with x1. That is, span of y comma x1 is not equal to the full space x, and so we can choose an element from here x, but not in span of y comma x1. Okay, that is, x is an element of x, but x is not an element of span of y comma x1. Okay, then the line segment joining this point x1 and x1, that is tx1 plus 1 minus t into x, is not an element of y for all t in closed interval 0, 1 or open interval 0, 1. Okay, this is true. If not, what happens if this is not happen? If not, suppose if there exists some point s, if not, let y equal to tx1 plus 1 minus t into x is an element of y for some t element of open interval 0, 1, then we can write this point 1 minus t into x is equal to y minus tx1. This implies x is equal to y minus tx1 divided by 1 minus t. This is equal to 1 by 1 minus t into y minus t by 1 minus t into x1. This is an element of span of capital Y comma x1, but this is a contradiction to our choice of x, right? A contradiction to our choice of x. Therefore, we conclude that the line segment joining x1 and x is not in y for all t. Therefore, tx1 plus 1 minus t into x is not an element of y for all t element of 0, 1, and so for all t element of closed interval 0, 1. Similarly, as x not an element of span of y comma x2, we can see that we can see that the line segment joining x2 and this point x is not an element of y for all t element of closed interval 0, 1 as before. Now we have to prove that If X is a normal space, then the complement of Y is connected. Okay. Now suppose that X is a normal space. And if possible, suppose the Y complement is connected, that is Y complement can be represented as union of S1 and S2, where S1 and S2 are disjoint, non-empty, open subsets of Y complement. Okay. Now consider a point x1, element of S1, and x2, element of S2. Then x1 is an element of Y complement and x2 is also an element of Y complement. That means x1 is not in Y and x2 is not in Y, but x1 comma x2 is an element of X. So by what we have proved above, there exists a point X in X such that the line segment joining x1 and this point, that is tx1 plus 1 minus t into x, is not in Y for all t element of open interval 0, 1, and tx2 plus 1 minus t into x is not in Y for all t element of open interval 0, 1. That is minus tx1 plus 1 plus t into x is not an element of Y, means it is an element of Y complement for all t element of this is actually closed interval 0, 1. We can also write it as open interval 0, 1 also, since x1 and x2 not in Y. This is true for all t element of closed interval minus 1, 0. That is, in the first equation we replace t by minus t, and so as t ranges 0 to 1, we get in this case t ranges over minus 1 to 0, and we write the second equation as it is and tx2 plus 1 minus t into x is an element of Y complement for all t element of 0. Now define a function alpha from closed interval minus 1, 1 to Y complement as follows. Alpha of t is equal to minus t x1 plus 1 plus t into x if t is an element of minus 1, 0, and this is equal to t x2 plus 1 minus t into x if t is an element of 0, 1. Okay. Then alpha of minus 1 is equal to, when t is equal to minus 1, what we get? We get x1. Okay, this is an element of S, and alpha of 1 is equal to when t is equal to 1, we get what? x2 is also an element of S2. This is an element of S1, x1 is an element of S1, and x2 is an element of S2. Also, alpha of 0 is equal to, when we check here, t equal to 0 means this is equal to x, and it also here t equal to 0 implies t equal alpha of t is equal to x, means that alpha is continuous on -1, 1. Then we can write closed interval -1 as alpha inverse S1 union alpha inverse S2, where alpha inverse S1 and alpha inverse S2 are two disjoint non-empty open subsets of Y complement. Okay, because we know that S1 and S2 are open, and so inverse image of S1 and S2 under a continuous function is always open. So alpha inverse S1 and alpha inverse S2 are open, and clearly this is non-empty since alpha of -1 is an element of S1 and alpha of 1 is an element of S2, and they are also disjoint. Since S1 and S2 are disjoint, we get the inverse images are also disjoint, and this means that of course disjointness can be proved as if some point if Y is an element of alpha inverse of S1 union alpha inverse of S2, sorry union alla, and means that alpha of Y is an element of S1 and S2, means that S1 intersection S2 is not equal to empty, a contradiction. Therefore, we get alpha inverse of S1 and alpha inverse of S2 are disjoint. Okay, so this means that closed interval -1, 1 is not connected, since it can be represented as two disjoint union of non-empty open subsets. Okay, but we know that closed interval -1, 1 is always connected. Okay, so just say contradiction. Therefore, our supposition is wrong, that is complement of Y is connected. That's the proof. Thank you.